So with this, we are going to start the program. Dr. K.S. Viswanathan is actually a good friend of mine. Dr. K.S. Viswanathan, I knew him much earlier. In fact, he did his BSc and Masters from Viswanathan College here, and he did his PhD from Vanderbilt University in US. Then later, actually, he was, I've heard of him earlier, in the chemistry group of IGCA, Indira Gandhi Center for Atomic Research in Kalpakkam. And of course, he has a lot of interest not only in research and teaching. So I forced him to move to a place like IISER Mohali. I don't know how many of you have heard of it. It is Indian Institute for Science Education and Research near Chandigarh, which is Mohali. There are several such institutions where undergraduate teaching is being now done all over India, many places, Pune, Trivandrum, Tirupati, various places, Calcutta, various places, and IISER Mohali is one of them. It's an outstanding place, many of my friends are also there. So after serving in that, he actually was sometime in IIT as a visiting professor. Now he is also visiting professor at Kriya University, which some of you might not have heard, and I will just mention it. It's near Gummidipuni in the Andhra side. It's on the border of Tamil Nadu, but it is on the Andhra side. In fact, I also go there to do the teaching because I'm also a visiting professor there. But he is a visiting professor for several years there. And he has been handling the chemistry through experiments. And he was kind enough to accept our invitation to talk about chemistry. He has a passion for it. And to tell about experiments. We are also interested. In fact, some of us have also talked about chemistry in the kitchen. Okay, that kind of thing. So there are several things. Chemistry is kind of activity human beings always involved without being called chemistry. But now we have to go a little more systematic about it. How things happen, why things happen and stuff. Even things like sculptures, metallic sculptures are made, uses a lot of chemistry and various activities of that kind. And now we have much more systematic, good understanding of chemistry, both from theory and experiment, like all other science subjects. They are linked with science, so always linked with theory and experiment. And he is going to talk to us about chemistry through experiments. Okay? Now I welcome Dr. K.S. Viswanathan to take the stage. Please. Do you have a card? Okay.
Thank you, Professor Govindarajan, and thank you, Science Forum, for inviting me to participate in this popular science lecture series. It's a pleasure to talk to students on topics of science. What I'm going to be doing today is doing a few chemistry demonstrations. And we will see how to arrive at the mechanism or the principles behind it, not so much by using reactions and formulae and so on, but by using a certain common sense approach. And mind you, at the end of the day, chemistry is common sense approach. Chemistry is not just writing out structures and formulas and so on. It's a way of bookkeeping chemistry. So I always say, chemistry is not 2K4 plus 15 HCl gives 2KCl plus 12. No, that's not chemistry really. That's only a way of bookkeeping the principles of chemistry that we have learned. The question that chemistry addresses is, why do these reactions happen? What are their rates? Can I speed them up? Can I slow them down? What's their relationship to the reactivity and structure and so on? Those are the questions that chemistry really addresses. And many of them, you will see that most of them, in fact, have a very common sense approach to the whole problem. And today I'm going to do these experiments. And together, we will see if we can find out why is the reaction going the way it does by simply using a common sense method. I will put up equations and the structures and so on for those of you who are interested. But again, I'm emphasizing that is not the real thing. The real thing is the common sense approach. when we study chemistry at a very early age, like in schools, we are often tempted to believe that chemistry is a subject where you have to memorize. How many of you disagree with me on that? In chemistry, you have to mug up. How many of you disagree with me? How many of you agree with me? That chemistry is just, you have to memorize. You will see, yeah, in any subject, there is a certain amount of memorization that you have to resort to. If you have to call your friend by his or her name, you have to memorize the name. There are certain things where you have to memorize. But that memorizing the stuff is not the essence of that subject, and that is what basically, and we will try to understand today. So I went to 5 experiments, and I would like you all to participate with me actively in that. They ask questions, because he said, that I will ask you questions. The question is not to find out how much you know. That's not the issue. The question is to see whether we can find out what is happening in this. And if you have a point of view, don't worry if it is right or wrong, just say it. And we will see how to go about the whole thing. Now, in all these experiments that one does, you always need help. And right now I have my colleague from Kriya University, Nagarjun, who is in charge of our lab and takes care of all the lab activities, the lab courses and so on. And he's really good at that, and he is here to help me in conducting these reactions. So, big thanks to him for helping me in all this. So we will start off now. The first reaction, and mind you, most of these reactions I'm going to be talking to you, maybe you have seen it, it's all there on YouTube. I'm not doing anything that's come up completely out of the world, no. But we will see how to turn down that problem, as I said, and see whether we can analyze it through this common sense approach that I'm talking about. So we will do 4 or 5 experiments depending on how much time we have. And if I cannot do all of it, I don't think that's a big deal. I'm sure they will give me time sometime later, and I can then come back and do it for you. The first thing I'm going to be doing is the blue bottle reaction. I'm very sure that you might have seen that. And what Nagarjun has already done is he has added the reagents in it. Basically, this is just water. And he has added some sodium hydroxide because I need a basic solution. And why do you need a basic solution? That's the details of the chemistry. But then he has also added glucose in this. So this is basically a basic solution of glucose. Now what he is going to do is he is going to add a small amount of a dye. It's a blue dye. It's called methylene blue. I will show you the structure for those of you who are interested in it. But knowing the structure is not the issue now. What he will not do is the following. 1 minute. Before I get started, slide. Yeah. Next one. Because this is extremely important before I start. Oh, where is that? Oh, absent-minded. Sorry. So, as I said, I'm from Kriya University. And that's the pictures will be there to see that.
இந்த ஏரியாவை தனியாக ஃபோக்கஸ் பண்ண முடியாது ஸோ ஆன் பண்ணி ஒரு ஏரியாவும் பிரைட் ஆகும்
And that's the library, the academic block, and that's the chemistry laboratory that we have set up, where we have undergraduate teaching and takes place. Now, before we start these reactions, I have to tell you a few things. There are certain safety processes that you have to practice when you do chemistry. And I'm very sure your college and school, wherever you do this, will emphasize on this. And this is extremely important. First thing, when performing an experiment, one would have to practice all required safety protocols. Wear protective eye goggles, laboratory coat, and shoes. As of now, I'm not having eye goggles, I'm not having a coat. Therefore, I'm not right at this point in time practicing safety protocols. Now, he's going to help me to do that. I deliberately told him I will wear it, get him just to emphasize the point that you have to have the, not even unbuttoned. Yes, first thing you have to unbutton the coat. So wearing the coat, there are 2 advantages to that. One, it's safer, so that if you spill any chemical, you don't really hurt yourself. And point number 2, you look a little more dignified as a absolutely important. You have to have safety goggles when you do these experiments, because if there is a spill, and mind you, for anywhere else, it's going on your hand, on your cheek, on your feet, it can be treated. Any spill into your eye, you probably are going to suffer it for the rest of your life. And therefore, it's extremely important that when you work in the laboratory, you always have these eye goggles, safety goggles. If it is not supplied, buy one. Just buy one. This is far less expensive than your eyes. So have this before you do any of these experiments. And just to impress upon you, both of us have done. So we are practicing safety protocol when doing these experiments. Do not perform these experiments at home. What happened? And of course, I was telling this more for the school students or people who are too excited about what they see over here. Please do not do these experiments at home without proper supervision, because some of these chemicals can be toxic, they can be corrosive, and so on. And therefore, it's extremely important that you perform these experiments only under the supervision of your teacher, or if you an expert in chemistry, like a laboratory instructor or so. Chemistry experiments are a lot of fun, there's no question about it. But then they must be done with proper care. So I thought I should say this before I start doing these experiments, and that's absolutely important that you follow safety practices. Okay. You already added? Yes. Can you hear me at the end? Okay, then I think I will not carry the mic. She has already added the dye, and therefore solution has turned blue. There is nothing surprising about it. I added a blue dye, and the solution has turned blue. And if I'm going to tell you that this is my demo, I don't think you're going to be very impressed by it. I have to. Yeah. So this is my solution, and therefore that is not the impressive part. And if this is what I'm going to do and go home, I don't think you're going to be very impressed by it. But let's leave it there for a while and see if anything happens. And I hope something happens. And this is one thing that our magicians, for example, they're always worried that their act should, come about the way they expect it to. So we very often keep worrying whether this will. Do you see anything happening?
You may want to use the mic because it is recording of this.
Oh, I see. Oh, okay.
The mic is there.
Yeah, okay. See, therefore it's become blue. I mean, the blue solution has turned colorless. I didn't do anything to it. I just left it there and it turned colorless. But that's interesting. That's much better than showing you a blue solution after adding a blue dye. But here this has become colorless. But then, and I get the color back again. And if I leave it for a while, you can see what's going to happen. I want you now, when this becomes, whatever happens now, I will show it to you. And I want you to make some observations. Mind you, in any scientific experiment, that's got nothing to do with just chemistry, whether it's chemistry, physics, biology, computer science, electronics, whatever, any experiment that you do, the first important thing is for you to make correct, unbiased observations. So we will see whether we can get this thing to go. I will show you the solution once something happens. It was blue, it became colorless. I shook it, it became blue, and I'm now waiting to see if anything happens. Starting to get lightish color and back again. So in other words, this reaction is showing you an oscillatory behavior, but the oscillation is actually forced. After going from blue to colorless, if I just keep quiet and keep watching it, it's just going to stay colorless. But if I shake it, it becomes blue. But now, I'm going to show the solution to you very carefully. Can you give me all possible observations that you can make in this? One thing is that the solution has become colorless after a while. Is there any other observation that you can make?
Can I read one thing? He actually, for some people who came slightly late. We usually start the program within few minutes of 4 o'clock, okay, just for your convenience. And just, I'm repeating, he added sodium hydroxide,
Glucose,
and a
then
dye.
and then the
Dye
dye
is
is showing
blue
oscillation
dye.
from blue to colorless, and when I shake it, it again becomes blue, and now it again becomes color. So the colorless part is spontaneous. It becomes colorless of its own accord. But to bring it back to blue, I have to do the shake. I have to put an effort into it. But if I leave it again, it's going to go colorless. But before I shake it and make it blue, is there any observation that you can make in this? Is there anything?
There's a light bit of color on the top, the surface.
Yeah, the surface there is a slight blue color. So while the rest of the solution has become colorless, the top surface continues to stay blue. So these are little observations that you must actually make, because when you try to interpret this later on, these are the observations that will come in handy for you. And mind you, in any scientific methodology, how do you analyze a problem? You know, you do an experiment, you make an observation, and after having made an observation, and as I said, the observations must be accurate and unbiased. Why am I saying this? It's a very trivial thing, you know, actually when you look at it, you know, why would you make a biased observation? But there are instances where people make biased observations because they think something should happen. They are already, you know, have a preconceived notion, and then they start looking at those observations that is in keeping with what they think. And this is not very uncommon. That's the reason why I am making this point, that you have to make unbiased observations. This is an unbiased observation. Solution becomes colorless when left alone, it becomes blue when I shake, but the top layer continues to stay colored, and therefore we keep all this in mind. And then, how do you go about with the scientific analysis? You make an observation, and based on that observation, you come up with a hypothesis. You say, okay, if this observation has to be right, maybe this is what is happening. You give a scientific theory to that. It's not yet a theory, it's still a hypothesis. And then what do? You say, okay, if my hypothesis is right, then I must expect something else to happen. I predict. Then you go back and check whether the prediction is coming out to be right. If it comes out to be right, then your hypothesis is probably correct. I'm using the word probably because you must do this one number of times to ensure that you really, that is good science. So you make an observation, a hypothesis, you make a prediction based on the hypothesis, you go back and do experiments to check if the hypothesis is right. If it is right, then you're probably right, and then you make further hypotheses, further predictions, and so on. And then finally you come up with a law, and that's the way science grows. So we have made two observations. Now, we don't still have enough information to come up probably with a hypothesis, but I can keep doing this experiment over and over and over and over again and see whether anything shows up. Now, for this, I'm going to give credit to my granddaughter, because the first time when she wanted me to do this, see, normally if you are seeing this reaction, they are not doing it, but they normally do it in a glass bottle or a conical flask. But because she insisted on seeing it, I had to do it at home, and therefore I had to do it on a PET bottle. And the moment I did it in a PET bottle, a new dimension cropped up, and I will tell you what that is. Now, what we did was, we took this same experiment and started this at 3 o'clock, much well before you people came. And this bottle therefore has run through maybe about 20 to 30 oscillations. So every time it became colorless, we shook it, made it blue, went colorless, shook it, made it blue, for 30, 25, 30 oscillations. That has only gone through 2 oscillations. So this is about 30. Now I'm just going to give it to, just feel the bottle and tell me if you see anything. Just feel, don't open it. If you open it, my experiment is wrong. Just feel the bottle lightly. Do you see any distortion or anything in that bottle? Shape, okay. I'll just show it to some people.
Vishwanath, you can stay here. I will collect it.
Yeah, just yeah, don't open the bottle. Just
anyone
feel
wants
the
to see?
bottle and tell me if there's anything that you've observed, as opposed to this bottle. This bottle is nice and round.
Don't open it, that's all.
Yeah.
Sorry.
Okay. Okay, for those people who have already seen this, what's your observation now? We had already a few observations. forced oscillation is one observation, and then there's a blue color at the top, at the surface. And now what is the shape of the bottle?
Maybe some pressure is created inside.
Okay, the first part of your analysis is right, pressure. But is it pressure? When you say created, what do you mean? Is it pressure increase or pressure decrease? Yeah.
So, like in the first observation, we saw that the layer, top layer was blue. So I think there must be some reaction with oxygen.
Okay.
So the interface is being blue, and when you shake it, does happen.
So he has an hypothesis, and he has the observation, and he has made a hypothesis in keeping with that observation. Now we have the other observation, that the bottle has got a little distorted. When the bottle gets distorted, and it's sort of buckled in. Why would it buckle in? If it buckles in, what's happening inside? Somebody said pressure. Would you think it's a pressure rise or a pressure decrease? Decrease. Pressure decrease. If there's a pressure decrease, what can be the hypothesis you can come up with? Okay, something is consumed. You've got to be careful at this point that something is consumed in the air. There's a head space above the water, and there is air inside. And if something is consumed there, then naturally the pressure is going to drop. What is contained in the head? This is what I am saying. This is a very common sense approach. You don't need even to know chemistry to come up with this conclusion. Now on the top here, what is the constituent of air? What's the nitrogen and oxygen? How much of nitrogen? 78%. And how much of oxygen? About 20%. Taking, what am I really doing? I am forcing the oxygen in the air to become soluble in water. There is a certain solubility of oxygen in water. But the oxygen has already been used up in the earlier reaction. So now when I shake, what am I doing? I am getting the oxygen in the head space to dissolve in that water, and then that reacts with the dye and makes it again blue. But what does the glucose do? Again makes it colorless. One more shake, what are you doing? You bring that oxygen back into the water with a certain solubility, it reacts, and therefore it becomes colored again. And this goes on. But as you keep doing this, what happens with the oxygen? It gets consumed. The pressure drops. As the pressure drops, it buckles. If you did this reaction in a conical flask, you would not see this buckling. But because you are doing this reaction in a PET bottle, you are able to see this. And therefore, you can start using this as your common sense approach to address the problem. And therefore, all thanks to the 6-year-old who made me do this in a PET bottle. Okay? Yeah, I don't know, these little kids, when they ask you these questions, some of them are really wonderful. You might not have thought of it, but they will force you to think in very many different ways. And that's basically what it is. Okay, now we have come up with this conclusion that oxygen is the reaction, and therefore chemists would say this is a redox reaction. Okay. Now if this is true, then his argument is right. Because at the surface layer, it is already in contact with the air, and therefore the oxygen is dissolving the surface layer and keeping that surface blue, because it is already converting it to the blue form. So far my hypothesis seems to be right. Now I can't do an experiment here, but can you suggest an experiment? This is my hypothesis based on your observation. Now based on this hypothesis, let me do one more prediction. And what could that prediction be? To show that this is absolutely right. Give me an experiment that would show that my reasoning so far is right.
Heat up.
Yes?
To heat up the
Heat it up.
heat up the solution.
Okay, that might speed up that reaction. But I would still not know. What's the other reaction? The issue is between nitrogen and oxygen, right? And I've said that since nitrogen is less reactive, nitrogen was not taking part. Now, can you do an experiment that you could, yeah?
So can I say in Tamil?
Any language, go ahead. Yeah, Tamil பேசுங்க பரவாயில்லை.
இல்ல அந்த ஆல்ரெடி 3 o'clock பண்ணி வச்சிருந்தீங்களா அந்த பாட்டில் ஓபன் பண்ணி நியூ கம்மிங் ஆக்சிஜன் வந்து ஃபுல்லா பண்ணலாம்.
Now let's open it. See that bottom? Just sound it. So it's opening up, undistorting that bottle. Now if you start doing it, you can see the color is getting a little darker because I now have more oxygen in it. Earlier it was turning out to be much lighter. Yeah, that's an extremely good point that he has made. I love point another. Anything else that you can do on the same lines that he did? He said, open the bottle, let the oxygen inside, and see whether the reaction starts all over again with that much more intensity. Where is that?
Sir, removing the oxygen and make it vacuum. So that
Oh,
they
that's also a good point, but the problem is vacuum is that if I put it up to a vacuum pump, the water inside will just boil off. So even though that's a good thought, no, I have experimental difficulty showing that. Anything else?
Can do it in another bottle. If you show a matchstick.
Doing it in nitrogen maybe.
Supposing I have a nitrogen cylinder, I just bubble nitrogen through it. Very intensively I bubble nitrogen. What will happen? The nitrogen will go through the water, it will remove all the air on top, all the nitrogen and oxygen is gone. And now if I shut up the bottle, what will stop at the bottle? What will I have inside? Only nitrogen. There is no oxygen. So once that solution has become colorless, there is no more oxygen to make it color, and therefore you will find that the reaction just stops at that point. That proves for me that nitrogen is not playing a role, therefore it has to be the oxygen, and therefore this has to be the redox reaction. After you have come to this point, so far mind you it's common sense. After you have come to this point, yeah, now we'll have to go into the chemistry of it, saying what does the glucose do, what does the oxygen do, and so on. These are details, and details which you must get into if you are a chemist. But the point I'm trying to make is, even if you are a non-chemist, up to this point you can come and actually give a theory as to what might be happening in this whole process. And this is the point I was trying to emphasize to begin with, that most of the chemistry problems that we look at, very often the initial phase of it would be just common sense approach. It is the nitty-gritty that you want later, the details that you want, that you may have to go into mechanisms and so on. For example, he talked about heat. That's also another thing, because when I do the heating, what will happen? The reaction will speed up. And we know why the reaction speeds up. So I can see how the reaction can be speeded up, and so on and so forth. Okay? Or I can do another experiment. I can fill it up with oxygen. If I fill it up with oxygen, what's going to happen? I'm going to get an intense color because now there's more oxygen, and therefore this whole reaction will work with that much later. So this is the glow bottle reaction, which is, it's there on YouTube and so on. But what I want you to look at is the way we analyze the problem in a very simple-minded approach. Of course, once I have done that, takes a while. Slow kinetics. That's the experiment. That's the bottle, and then we put glucose, sodium hydroxide, and then we put the cap, and we get started, and we did all of that. And the overall reaction is glucose reacts with the dye, the original form, which is blue in color. The glucose itself would get oxidized, and the dye would get reduced, which is colorless. And then when you have oxygen, that reduced form of the dye, these are the structures. If you're not interested in these structures, if you're not interested in the reaction, it doesn't matter. But if you're a chemist, you would want to get interested in these reactions. And therefore, this is for everybody. But the point is that you can actually use very, very common sense approach to all this process. Okay. Any questions on this, or any discussion, or anything else that you want to add to what we just said? Yeah.
You can also incorporate kinetics into this.
Absolutely. Absolutely. You can incorporate kinetics into this, you can incorporate interference with something else, and so on. And therefore, in any chemistry reaction that, the reaction itself might be simple, but if you start looking at the details of the whole process, it can lead to an entire set of complexities. And sometimes it can keep you busy for a few years doing research on these reactions. Yes, the kinetics of these reactions is extremely important. Do it in water, do it in a different solvent, see what happens, and so on.
Here itself you can add some more water and monitor the time taken for the color change.
Just like basically, vary the concentration of glucose, vary the concentration of sodium hydroxide, and so on. And vary the concentration of the dye itself. Because lesser the dye, it's going to take slower for the whole process to happen. So the kinetics can be done simply by varying the concentration of glucose. See whether sodium hydroxide has an effect, see whether the dye has an effect. And that's how the kinetics is actually done. Okay.
Can we change the dye?
Yes, you can change the dye. The only thing is, the dye must have a redox potential such that it can react with the oxygen at room temperature and change its color. If that is not facile, then it's not going to happen. See, dyes usually have the redox chemistry that goes from one color to the other. But how easy is that redox going to be? If that redox reaction is easy, like in this case, then you will see a visual effect. If you don't have that visual effect, then the demo doesn't really work well. And therefore that might. But in principle, your question is right. Can I think of another dye? Yes. Provided the change in color of the dye can be affected by oxygen under ambient conditions.
What about salty water?
Fun?
Salty water will be good.
Salty water. Yeah, so if you have salty water, in this case it does not affect you so much. I'm just giving you the answer, but there will be another reaction that I will show you, and I will also give you a little history or some anecdote where salty water actually has a very serious effect on the whole process. Okay. The next one is another very simple reaction, which again many of you have seen, but I'm going to do it and we will see another concept in chemistry that can be thought of when you do this. And that's the whole process of developing toothpaste that we, and what Nagarjun is going to do the reaction. So we didn't want to spoil the tables and chairs for the library, so we have all these little, and what he has inside is hydrogen peroxide and some detergent. Okay. This one, he's adding the detergent now. And hydrogen peroxide, is it a stable compound, or what will happen to hydrogen peroxide if you buy and leave it around? It will decompose. It will just give you water and the oxygen will go away. So it's not a very stable compound, but it is stable enough that you can keep it in a bottle for some time. And that's the reason why we have it. And he's just adding a detergent for the site. And you see nothing is happening now. So just one moment, just add, don't add it inside, just put it on the side. The dye is only for visual effect. The dye has nothing to do with the experiment. So what he has basically done is put hydrogen peroxide in that flask in this measuring cylinder, and he has added some detergent. And what will detergents do when you agitate them? You will get foam. So you know why he's added. He wants foam. So he's added the detergent to get some foam. And so far nothing is there to see. He's done the solution and the peroxide and the detergent. And now he's going to add something. In other words, the decomposition of peroxide. Now just imagine, if the peroxide was decomposing and liberating oxygen, and the oxygen wants to come out, what will it do? It will churn the solution. And when it churns the solution, what should happen to that solution? It should foam. But there is no foaming. Right, there is no foaming. So which means the peroxide is not really decomposing. So now what he is going to do, he is going to add a little solution. I'll tell you what the solution is a little later. Just add it. Suddenly there is a foam. So what does this mean? Oh, look at that. Don't come up, don't come up. Good. I think if you're old enough for the chemistry to listen to you. Yeah. So what has happened here? Nothing happened for quite some time with the peroxide and the detergent. Nothing happened. But the moment he added a solution, and the solution was a very, very benign potassium iodide. And that's it. It was potassium iodide. And it got nothing to do with anything, the whole reaction. What potassium iodide did was it acted as a catalyst for the decomposition of peroxide. So he asked a question about kinetics, he asked a question about kinetics. Very often, why do we study kinetics? We study kinetics because we want to know the rates of the reaction. And if the rate is slow, and the industry wants the rate to go, industries always want the rates to go fast. There is no point in making a medicine which you can make at the rate of 1 kilogram per year. That's not feasible at all. You want to make it quickly enough to make profits. So they always will ask you to, is there a way to speed up my reaction? So therefore you study kinetics, and if you have to speed up your reaction, we know what to do. We have to think of a catalyst. And many of the industrial processes, mind you, use catalysts to speed up their reaction so that they make it industrially viable. That is the situation over here. Peroxide was not willing to decompose under normal conditions. Even though it's not very stable, it decomposes at a very, very slow rate. But the slow rate is visually very unattractive. So what did we do? We just added a small amount of potassium iodide. And once you added potassium iodide, the decomposition just took off in a big hurry. And then what happened was that the oxygen came out in lots of quantities. It churned up that solution, and when it churned up that solution, you had foam. And therefore you saw that foam. So in other words, what we are really demonstrating here is the whole process of chemical kinetics being speeded up by a catalyst. And we know how a catalyst works and why a catalyst works the way we do and so on. So if any time you want to introduce the concept of catalyst as a teacher, this is the best reaction. Do this first, talk to them about catalyst, but they know what a catalyst does because they have seen it, and then you start telling them what catalyst is, they will listen to you. But if you start off on day one with the catalyst is something that speeds up the reaction, it affects the potential surface and blah blah, nobody is going to listen to you. First show a demo, tell them how the catalyst works, and then talk to them about the chemical principles behind how the catalyst actually works. Any question or any other suggestion or any things that you have?
Sir, 1 minute.
Yes.
We can prove that oxygen is trapped inside the foam. We can do that.
Yeah, we could, because what you can actually do is, we could have a test for oxygen by putting a little splinter and so on. But
Or even a candle will do.
yeah, but then what Nagarjuna and I did was, we decided that we are not going to have any experiment with flame, or in fact there was one chemical volcano experiment, but we decided not to do it. Because in a chemistry laboratory you can do all these things, but in a thing over here which is a library, we didn't want to set the library on fire and go away. And therefore we decided that we will not do any explosion experiment, we will not do, there are many interesting explosion experiments. But if you come to Priya, we will show it to you in the lab as to how it happens.
Start spraying water.
Yeah, and that's it, all will be wet by now. So therefore we decided that we would not. Otherwise what he's saying is right, if you have to show that oxygen is there, just have a candle, a split, a lighted splitter. It will catch fire and the flame would go on. And you would know oxygen is there, and there are many things that you can do. But many of these flame experiments and explosion experiments we said we would not do. So we chose those experiments which are harmless and which are quiet in terms of any explosions and no fire that is basically used. Now we will do the next experiment. Which one are you getting? Okay. Let me do that. The next one I'm going to do, I've been trying to learn jugglery for a while. So I want to see whether I can try that with you, and if it works, that would be good for me. So I've got three empty glasses. I've got these. Okay, just three of those. Okay. Now I'm going to pour water into one of these glasses, and I'm going to keep sharp in it. I'm going to ask you to figure out the one in which water is. And I believe that I am quite good at it, and you will not be in a position to figure out which one it is. I believe that. Okay, here is the water. I put water in this. You have seen that. Okay, now I'm going to juggle this, and I'm going to ask you to figure out eventually in which cup the water is.
First one.
It's like I'm not good at it. Let me try it one more time. Okay, let me just try it one more time.
Middle one.
I think it's not working. I'll tell you, just give me one more chance. Because I have practiced it so well, I thought I'm good at it, but for some reason, it isn't working. So I'm going to I pour the water into this cup, and I'm going to challenge you this time, that you will not get it. And my challenge is the following, that once you pick a cup, I'm going to take that cup and pour it over my head. Because if you are right, I am wet. But if you are wrong, then I know that I am getting there. Okay, now let's start. Ready? Sure? Yes. So I'll stand by my promise. I got you this time.
சார் அது ரெண்டையுமே நீங்கள் கவுத்தி காட்டுறீங்களா? இல்லை, I had one hypothesis that you may have.
But let me answer your first question.
Then my hypothesis is correct. What I had a hypothesis is that அந்த கப்பில் நீங்கள் ஏதோ கெமிக்கல் வச்சுருக்கீங்க which evaporates the water. So you delay, you want to evaporate it, so you delay by your conversation.
He's got most of it right. See, I'm not a juggler. Nowadays pretending to be a juggler. I'm not. You know, I can't even move the cup properly, and you could see. You know, I mean, it was. You know, this is the thing they play with cards, right? And if I were to do that, I'd be losing every day. So I'm terrible. But I still challenged you because I knew that in the third attempt, I'm going to play a trick on you. So in the first time when I put the water, it was into an empty cup. In the third time when I did it, that cup already had some chemicals inside, as you correctly predicted. And that chemical did not evaporate the water, but that's why it was a little different. But the idea is, yeah, that cup actually contained sodium polyacrylate. Now, sodium polyacrylate is a compound that absorbs water tremendously. In other words, 1 gram of sodium acrylate can absorb 100 grams of water. And he's extremely observant. He's also right when he said, you are making unnecessary conversation with us. he's really sharp. You are making unnecessary conversation. I was making unnecessary communication. I wanted to make sure that that water got pulled up by the acrylate. Because if I did it too quickly, I would be wet. So I had to play, a few seconds, not terribly, just a few seconds. But I just want to make sure that I don't go home wet. And that's the reason why I played a little, I was just basically talking gibberish. I was not even telling you anything useful. I was just talking.
Silica gel.
That was polyacrylate. So, silica gel can do it, but polyacrylate is extremely absorbent. And 1 gram of polyacrylate can absorb roughly around 100 to 300 grams of water. And what does that polyacrylate do? And that, mind you, okay, now that I have said this, if you are an entrepreneur, where would you use this polyacrylate? The diaper industry. And people have already done that. Because in the diaper industry, you want to absorb the water immediately. And therefore, the diaper industry actually uses polyacrylate. And which is what I did. And I know for a moment I got you. This guy was going. I know you were all extremely happy. This guy is going to go wet today. But that didn't happen. Okay. Yeah, that's the structure of polyacrylate. It doesn't matter that what the structure is. It's got a negative part of the molecule and a positive sodium. So what the water does is displaces the sodium and gets trapped in it. And then we are all chemists and physicists and biologists have studied hydrogen bonds and so on. The water gets trapped inside all of that. And therefore the water is totally immovable. I have trapped it. And if you actually look at it inside, you don't graph up. Oh, nothing like this. Like a gel. It basically forms a gel, and that's how the whole thing happens. So therefore, that was the reaction in which I essentially trapped water. And instead of just showing you the polyacrylate, putting the water inside and showing you that it forms a gel, I just thought I would play a little mimic a little game and put myself in a very difficult situation, saying that I'm going to double and so on and so forth, just to get you interested. But the point is there was chemistry in it, and the chemistry there was that here's a molecule that can trap water 100 times its capacity, and therefore that could be used it is used in the diaper industry and many other industries where you have to hold back water and you need to form a gel.
Can I ask you a small question?
Yeah.
In people sell the drink called Madurai Jigarganna, where they use the badam resin, which is actually a gum from the badam tree, and they pour water and keep it for some time. And after some time it becomes gel, like what you showed, exactly like this.
Yeah.
Is there also
So
some
chemistry would be very, very similar, because again that would have a network of molecules in which the water would get trapped in between and they will form. See, any gel, that's what it does. As a dry powder, it has got places where it can store water and trap water by either ionic interactions or by hydrogen bonding interaction. And once it does that, and depending on how well you have structured that powder, you can trap an enormous amount of water, and this is what it is. So polyacrylate is extremely good at that. But the one is
So actually you can buy this badam resin and try. Within 1 hour it becomes a gel.
And that's the thing. Sometimes what happens is kinetics again when we come to kinetics may be slow. So the water has to diffuse inside, it may not be so easy. So the kinetics may be slow. The polyacrylate, the kinetics is very fast. I didn't trust it, that's why I did that loose top for some time, just to make sure that it got gelled up. But the point is this. Okay, how much more time do I have? Okay, I'll just do one more, we will do the okay, we do it then.
Some of the target came late. Yes.
Okay. Now we're going to do see the very first reaction, we saw oscillation, the blue bottle, where we had a reaction going from blue to colorless, and then from colorless back to blue. But that part of the reverse reaction, we had to force it. It was not a spontaneous oscillation, it was a forced oscillation. It's almost like a pendulum wanting to go to one end and then it stops. And you have to push it and then it comes back and again comes and stops. So every time you have to keep the pendulum in oscillation, you have to keep it pushing every now and then. But pendulum doesn't work that way. The pendulum actually has spontaneous oscillation. And what we're going to do now is show you a reaction which actually has spontaneous oscillation. And we will see. And when I show that reaction, I will address the question that you asked earlier about sodium salt. And so what he has done is he's already mixed a few solutions. We won't worry about what he has mixed. Let's first get this reaction. Then we will try to address it through common sense approach. And then we will come to the nitty-gritty of the chemistry. So, start.
Yes, sir. Shall I come this way?
See that? Okay, I didn't do anything. So in fact, just to prove to you that I'm not doing anything, I leave it on the table and see what happens now. Can you all see the last thing?
Because
Yeah.
I can show you. I can show you. Color is oscillating between brown and dark.
It goes from blue color to an amber color, and then
Comes back.
stays there. And I'm not shaking it this time, my dear. And then it
Comes back.
So this is a spontaneous oscillation. No forcing. This is just like a pendulum. You pluck it and you leave it and it will go on. Will a pendulum go on forever? What happens? Yeah, there are damp, we call that damping, right? There are friction effects and air resistance and so on that will cause damping and it will eventually stop. The very same principle will happen here also. Don't expect this to go on for the next 20 years. In a few minutes from now or in a half an hour from now, you will see that the color change will happen less and less frequently and eventually it will stick onto some color depending on the concentration of the reagents and so on. But to begin with, mind you, it is oscillating. So now the question is, the first reaction was oscillating, but I had to force it to oscillate. In this reaction, I am not forcing it. It's doing a spontaneous oscillation. So why would something spontaneously oscillate? Why would the reaction go from state A, which is amber, to state B, which is blue, back to state A, which is amber, state B to blue, and so on and so forth? So the question therefore is, what is this oscillation? It is not exactly in a reversible reaction, mind you. A plus B goes to C plus D, and then C plus D goes back to A plus B. That's a reversible reaction. Yeah, you are.
So I just observed that first experiment நீங்க பண்ணும்போது வந்து மாலிக்யூல்ஸோட மோஷன் வந்து உள்ளுக்குள்ள ரேண்டமா நடக்கல. நீங்க ஃபோர்ஸ் பண்ணி அந்த மாலிக்யூலோட மோஷனை தூண்டுனீங்க. பட் இது ஆம்பர் கலர்ல மாறும்போது அந்த கிளியரா தெரியுது அந்த மாலிக்யூல்ஸோட மோஷன் தொடர்ந்து நடந்துட்டே இருக்கு. So it oscillates still அந்த molecules motion நிக்கிறவர்.
Okay. He's made a bunch of good observations for molecular motion, but molecular motion, mind you, at room temperature, molecules will move. Whether what we really see are bubbles and particles and so on. We can't see molecular motion, but we can infer molecular motion. And at any temperature, like room temperature, or even if you go to lower temperatures like 10, 5, minus, and so on, the molecules are in motion. And of course, quantum mechanics will come and tell you, even if you go to 0 Kelvin, they are not quiet. The world is never quiet. There is something happening even when you go to absolute zero. So molecular motion is there. But is that the reason for, in every reaction molecular motion is there. But why am I seeing oscillation only in this reaction? So something very funny is happening in the reaction. So what I will do is, I will just show you a little, let's look at a reaction scheme. If we had much, lots of time, we will try to discuss this slowly, but since we are running short of time, what I will do for you now is give you a reaction scheme, and I will tell you what might be happening. Let us say I have a reaction scheme. You don't need chemistry for this. A plus B going to C plus D. That's the reaction. And then C reacts with E and becomes F. So this is the reaction. But now, just imagine a situation in which C, we talked about catalysis, right, a little while ago. And what does catalysis do? Speed up reaction. Can you think of negative catalysis? Yeah. So in this case, what can happen? Supposing, let us say, C is the negative catalyst for that first reaction. So what would that do? A plus B gives me C plus D, but C is the negative catalyst for that reaction itself. So what would happen after a while? The reaction starts off in a jiffy, but then it slows down. So I produce C to begin with, huge burst, and then no more C is produced because the reaction has become so slow, or it is in fact stopped, because C is inhibiting its own production. But what is the next reaction doing? C is consumed. So the next reaction, let's say, has a rate which is reasonably good, and it consumes C. What will happen to C now? C will drop. Once C drops, what should happen to the first reaction? It will start again. It will again start and come to a point where C is in large excess, but then it will stop because the reaction has been negatively catalyzed. But then the next reaction consumes C, and therefore the C concentration will drop again. Again the first reaction will pick up. So now I have given C a blue colored star. So every time that C is formed, let us say that blue color is there, and then the reaction becomes so slow, so no more C is produced, and then C is consumed by the second reaction, and therefore it becomes colorless. And now there is no C to begin with, and therefore the first reaction will start all over again, and therefore this will go on. This is what we call as a negative feedback. So the C is inhibiting its own reaction. And mind you, in biology, I'm very sure there are biology students over here, this is seen very often. What does the body actually do? Sometimes it produces certain enzymes or produces certain hormones or whatever, but it does not keep producing it forever. At some point, the body knows that this is too much, so the very concentration of that enzyme would actually inhibit the production of that enzyme. So negative catalysis or a negative feedback is a very common affair in biology. It's a very common affair in many chemistry. It's a common affair in physics, electronics, lasers, and what have you. So this negative feedback is something that's very, very common, and it is a negative feedback that will cause the oscillations to occur. And what's the basis of the whole process? Something that is produced is inhibiting its own production. If that were to be the case, and then there is another reaction, if I didn't have the second reaction, the whole thing would have just stopped. But the second reaction is consuming C to trigger the first reaction all over again. And mind you, the kinetics of the second reaction has to be such that these things happen in real time scales. If the second reaction was very, very slow, what would happen? You would produce blue, but to get that amber, you have to come back tomorrow. But that doesn't happen because the second reaction is quick enough that it consumes the iodine, and therefore the first reaction starts all over again in quick time, and you see this oscillation. And that was not happening in the first reaction. The first reaction had to force the oscillation. Over here, the oscillation has been set up because of this negative feedback that there is. In other words, while we looked at catalysis as the process in the hydrogen peroxide decomposition, here we are looking at the process of negative catalysis, which is actually causing these oscillations to occur. And negative catalysis, like I said, is a very common affair in biology. There are many situations where otherwise the body would simply keep producing an hormone forever. That is bad. It knows when to stop, and it is a negative catalysis or a negative feedback that causes the concentrations to stay where they should be. And once that is consumed and the concentration drops, it will again produce more of it. For example, insulin. Body doesn't keep producing insulin forever. It produces it on demand. And therefore, very, very similar thing happens in many, many biological processes. And this reaction, mind you, is not simple at all. This was done by two teachers, Biggs and Rosher, to demonstrate chemical oscillation. But then that's all the reaction scheme. Go to any Google search and you will get all the details of this reaction. I don't want to spoil the whole fun of this thought process by giving you this nitty-gritty. But this nitty-gritty is important for you to understand in great detail. This experiment is not a simple experiment. When I say that C is preventing its own production, it's a very complex process by which it stops that production. In this case, there are two different types of mechanisms, ionic and radical. Radical takes over sometimes, blah, 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 and goes on. But the point is, the production of C inhibits its own production. And that's the reason why you have the process.
It's like coupled oscillations in the mechanical system.
Yeah, coupled oscillations in mechanical system, that's very, very true. But in a coupled oscillation, energy keeps going from one to the other. Here what is happening is I'm draining away one, but the net effect is the same. It's like when I have two pendula that are coupled, then I have just pluck one and leave it. That will oscillate for a while, and then that will stop, and this will oscillate a little while later, and it will go back and forth. Absolutely true. But there's an energy exchange between these two. Here I'm not really talking so much of energy exchange. The net effect is the same. The net result is the same. But the mechanism that is happening between the coupled oscillator and this reaction, that is different. In this case, it's a negative feedback. In that case, it's an energy exchange between the two oscillators. And that's basically what it is. I think I have just come to the end of my time. There is just one more.
Okay, 5:15. People ready for one more experiment?
Yes,
Are you ready for one more?
Yes, sir.
Okay, do one more.
Here we give
Okay.
like 5:30.
Yeah.
You have a question and
Okay.
answer session.
Give it to another thing. Yeah. Students are interested.
Oh, okay. Yeah. But you prepare that. He will just prepare one more experiment because but the question that you asked earlier, the salt, will it affect that reaction? In this case, it affects it in a huge way. Because it's Iron minus that is taking part in the reaction. If I have Cl minus, then that will really mess up with the whole reaction. And the oscillation actually does not even occur if I take water that has got contamination with chloride. And I learned it the hard way. What happened was, I was an educator at that time, and IIT Madras had asked me to come and do some demos for school children. So I had done this experiment for many times. So I took some of these chemicals. I said, distilled water, I don't have to take it to IIT Madras. IIT Madras will have distilled water. So I will take it from them. I don't have to carry. In fact, we carried 2 liters of distilled water here. So I can't expect Randall Engineering Library to give me distilled water. But IIT, I thought, this sort of problem. So I got everything done. I called up, the person who was helping me. I said, he gave him a bottle. I said, can you please get me distilled water in this? So he went out and came back a little later and handed me the bottle. I started the reaction. And as I told you, one of the biggest fears that I have is you start something and it doesn't work, and I keep looking at it. And I kept looking at it, the oscillation wasn't occurring. And there were all these high school kids, and mind you, high school kids can be extremely exhausting. So what are you expecting to see? What are you expecting to show us? I said, I can't tell you that because if I eventually get it to work, the fun is lost. Therefore, I can't tell you, but I still don't know why it is not working. And I kept staring and staring at it. And I didn't know why a reaction which I had done so many times and it had worked every single time now did not work. Then he called that person. I said, did you get me distilled water? And then he said, no sir, the lab is too far away, so I just went to the tap here and I said, no sir, I need distilled water. Can you please go get distilled water from me? Go to the lab and get it. So he went to the lab and got distilled water, came back after about 20 minutes, got me the distilled water. We did this reaction, it worked. That day I realized that the chloride can actually interfere. I learned it that way. Then I went back and checked the literature on this. And sure enough, people have studied this. And chloride does interfere with the iodide. So this is potassium iodide solution. It does interfere. And therefore, chlorides and bromides that you have will interfere and completely suppress the oscillation. So that can happen. So there are reactions where these things can happen.
Okay.
And
You want to switch off the light?
Yes.
okay, we will have to turn the lights off. Yeah, all lights off. And can you put a speaker on?
Don't be afraid.
Is there a way to turn that light off? Turn the. I don't know how effective this will be. This needs a real dark room for you to see it. So he has got some solution and just see what happens over here. And again he's going to add some peroxide. Most of the reaction that we have is based on peroxide. Yeah, it came out much better than I expected because normally when we turn the lights off and it's really dark, it shows up really well. Okay, and this is a reaction that is what we call, yeah, now we can have the lights on. And this is the last experiment, I will stop after this. This is what we call as luminol. It's a compound. You've got nitrogen ring, carbon ring, aromatic ring and so on. Forget all that. What the reaction does is, it takes that molecule and in the presence of iron as a catalyst, that means we have used copper as a catalyst, right? Yeah, you can use copper as a catalyst or iron as a catalyst. And there's a reason why I'm mentioning iron. If you use iron as a catalyst, then this reaction will occur. You get that brilliant blue color. And why does that happen? You take the luminol in the presence of iron and peroxide, it undergoes a chemical reaction and produces a molecule, a product, which is in an excited state. You know, any molecule in an excited state will drop to the ground state and give you light, right? So if I take wires, for example, a wire, and I heat it, it glows. Why? Because when I heat it, I'm taking the molecules from the ground state and I'm exciting it, and then when they return to the ground state, they emit light. So the same way over here, you know, the molecule is being produced, the chemical reaction has produced the molecule in an excited state, and then the molecule returns to the ground state, giving me that light, and we call that as chemiluminescence. When biological species do it, we call it as bioluminescence, and you will see fireflies. So they are actually doing reactions in which they produce molecules in the excited state, and when they return to the ground state, you have the color that is emitted, and that's basically what it is. Now the trick here, or the important thing here, is that the iron is the catalyst. So I showed you a little trick. I pretended to be a jugglery expert, you know, and I did that and I failed. Now if I were to, you know, commit a murder, which I have not done and which I won't do, and you see blood, you know, you slash somebody and there is blood, what's the first thing the culprit would do? Clean up that place and then leave. So you clean up that place and then leave, but the police then figure out that the murder must have been committed here, but there is no sign of blood there, because it's all been cleaned up. What they would essentially do, of course today they use other methods, but this was in earlier times. You actually can spray this luminol and peroxide. If blood has been present there for some time, you would have left behind some iron. Now iron as a catalyst will start to produce these molecules in the excited state and they will glow. So the moment you shine some UV light, you can actually see the glow. And many murder cases have been solved essentially by spraying luminol, peroxide and looking at it in UV light, and you will actually see the exact design of the blood stain. Even though the floor looks absolutely clean, the murderer cannot remove every trace of iron. He or she is going to leave behind something. And therefore the luminol experiment is actually an extremely good forensic tool to detect the presence of blood, and therefore it has been used by forensic experts to actually do that. So what I showed you was a classic case of chemiluminescence. It is academically very interesting because you're producing molecules in excited state and then you can look at the emission and so on and so forth. But it has useful applications in the forensic chemistry because it's a good test for the presence of blood. And there are people who, of course I won't do that because certain reasons, but there are people who will do the very same reaction, they want to make it very dramatic, they will poke that thing, get some blood out, put it on a slide, show this, and then show the blue color. For various reasons I won't do that, but that's the one way by which you can make the whole demonstration extremely effective. And therefore that's the luminol reaction. I think we'll stop here. I think we have done quite a few reactions. Because if we can come back later, there are other things that we can do. Do visit us at Kriya and we will show you many more reactions for you at that point in time. Thanks a lot. Do you have any questions?
We were ready with the question and answer session. Let me ask the participant to fill up the feedback form. So we have shared the link for providing your feedback. Please click the link and fill up the feedback form. This is the one first link. So I will also encourage you to leave your email ID and mobile contact details so that we will contact you for our future programs.
Yes, I have a question. How many of you are doing chemistry?
Yeah, we have one question.
Okay.
Can you use Castle-Mayer test to check the blood strains?
Can you find it?
Castle-Mayer test.
I don't know because I don't know the category. I've heard of it, but I don't remember it.
Anyone have any questions?
Sir,
Yes.
can this sodium polyacrylate be replaced with any natural product? Like sir said, one of the examples, Viswanathan, right?
Yeah.
We can add some other catalyst to absorb, so that it can absorb easily or fastly.
Yeah. I'm sure there are natural products that will do the job because nature, mind you, is extremely sensitive to the fact that water has to be absorbed, water has to be retained and so on. So nature does that. So I'm very sure there are, all these lignin and other materials, I'm very sure they can absorb moisture and so on. But if you actually go back and look at the way industries have developed, we always start by finding the required material in nature. Like, for example, if you look at quinine, the treatment for malaria, you have forgotten the bark of the cinnamon tree. But then, the point is, depending on nature, to produce the amounts of drugs that you need for the world, is not going to help you because the amount of material that is produced in nature is too slow. So very often you will find that what the chemist will do is to see whether I can synthesize that in the industry, in a laboratory. Therefore I can start making it in the industry because that way I can make much more than what nature can give me. So the route is always, you will get the idea from nature, but very often you will go back to the industry or the chemical laboratory to synthesize that molecule and then make it in much larger quantity. So to answer your question, yes, I'm very sure there are natural products which will absorb the water to a large extent. But can I depend on it for my needs? No. I might need chemical industries to make it for me on a much larger scale. And sodium polyacrylate actually fits the bill. Right?
It depends upon the application where you are.
Yeah.
Now, what's the amount of water you want to absorb?
And that, you need lots of material. If I were to depend on nature to give me,
Yes, the question.
yeah.
So it's bioluminescence is in bioprime.
Please,
There's
please,
in
madam.
jellyfish also. We
Yes.
have the same thing, that without some kind of a jellyfish like Grobotus,
Yeah.
namely that you have to, that they also have the same kind of things. But is it the same thing, parasite, the same chemical only they are using?
No, the chemicals may be, I think in the firefly, Luciferin.
But not that jellyfish is different. Right?
Different. But what you said is an interesting point that you raised. Because I don't know how many of you would have, at least I saw this effect extremely wonderfully in the sea. Yeah, and that too, the first time I saw it was sometime in 1990. Because I was actually living on a house which was on the beach. So you open your house, my door, and 200 meters out would be the sea. And one particular night we saw the waves were actually greenish blue. And we didn't know what the hell it was at that point in time. And of course, immediately there was all this talk going about, oh, the reactor people let out radium into the water, and that is why. And of course, I used to argue that if you let out radium into the water, it should be glowing all the time. It should not be glowing only on the crest of the wave. And of course, what I then did, I think my daughter would remember that we went to the beach and collected this water in a bottle, brought it back home, and turned off all the lights and shook it. And bang, the light would be emitted. And then little while later it would go. You shake it again, it would again emit. So it was basically the agitation that was causing the light emission. And that is also in some, there's a terminology called triboluminescence, where you convert mechanical energy or heat to light. And I then went back to read about this. And then I figured out what this, I forget the name of that organism now. What it essentially does is, when it is agitated in the water, it sends out this light more as a defense mechanism. So when there are other fishes that come to eat it, and there's agitation in the water, this puts out this light, which will scare the other fish away, and then it would use, basically using it as a defense mechanism. It's again the same thing, where the shaking causes the molecules to go into an excited state, and then it drops down, providing light, and that is basically the effect. It's again chemiluminescent, but it's got a more specific name called triboluminescence. Tribos is friction, heat to this thing. I've heard this, but I've not ever tried it. This candy, Kalkund. So if you break Kalkund, you can get a light emission. But that is again triboluminescence, where you are converting mechanical energy to light. We know in spectroscopy, I can convert light to heat, and that is the non-radiative decay. This is the reverse of that, where I convert heat to light.
Sir, any substitute for luminol? Because luminol is slightly costly.
I know. I think there are some molecules. Because if you go into the literature of all these demos, there are some compounds. But apparently luminol is the one that gives you the best effect.
But not out of
And therefore, I think there are. I don't remember the name, but there are.
So in between you said come to PR lab, we show you this and show you that. So what does that mean? I mean, you should come.
There are many other experiments.
No, I know that.
No, I'm just inviting you to other ones.
Oh, okay.
Yeah.
Is there any way that I can come there?
No big deal. All you have to do is you just let us know when you want to come.
Okay.
So that we can arrange for you to go around and see.
Okay. Cool.
And if you have my email ID, so we can get in touch with us. Just for you. And I'm just making more as a I'm being a nice guest.
Become a member
A
of
host.
the site, we'll make arrangement.
Yeah, I'm just trying to be a nice host. I can visit us and I can show you the way. It's a very new university, it's over 4 years old. It's a liberal arts and science. So
Can we have an industrial visit like
Pardon?
Can we have industrial visit, a similar thing to Kriya Lab?
Yeah, I mean, you can come to Korea Lab and you can post it as an industrial visit. That is between you and your funding agency. But they're perfectly okay. We will certainly entertain you. And
Any questions?
yes.
What is your view on radium as a jewelry one that you
As
radium as jewelry?
I don't get you.
Radium as jewelry.
Radium as jewelry. No, radium as it's all radium is radioactive. Therefore, you wouldn't want to use it as jewelry in any case.
Then she will become a Madame Curie,
Pardon?
She will become a Madame Curie.
So there used to be the old watches where they would say radium tipped and all that. I don't know how much of it. Huh?
That's called Mesatori.
Yeah. So, but radium light is radioactive, and therefore you wouldn't ever want to use it as a radioactive, as a jewelry material at all. That is to be.
You should be protected by all the.
Yeah.
The
Yeah,
blood cancer
it-
will come.
Yeah.
Blood cancer. The Madame Curie died of blood cancer
Right.
because of.
Yeah, because Madame Curie was,
all the
of course,
safety
it was
precautions.
exposed to a whole host of other things. She was exposed the pitch blend that she was using
Yeah,
to this thing, and that was she was exposed to a whole host of radioactive materials. Radiation safety was not an issue at that time because we didn't even know about radioactivity at that time.
Now we are.
Now we are, and therefore it would be not worth the while having.
No, it's illegal also.
Yeah.
Sir,
Any questions?
One small question.
Sure.
Which chemical would you recommend for a murder to erase all the evidence? From your experience, which chemical?
No, I have no experience.
With your teaching experience, would you recommend?
I'm not teaching those aspects. No, I see. He is asking a question that is perfectly fine. How to get rid of all the evidences and so on.
So don't give ideas.
Actually, I can answer that question.
He has experience.
No, it was apparently used in England by some kind of a Russian spy on the polonium, this thing which is added to your tea and takes effect much later.
The Russian opposition
Yeah.
leader was
Some accusations are there, but probably chemistry can explain it much better than
even that.
Arsenic poison. What another one is arsenic poison.
Arsenic poisoning can be figured out nowadays quite easily. Because we have analytical. See, arsenic in water, the WHO regulation is 5 parts per billion, which is 5 nanograms per ml, and 5 nanograms per liter. And therefore, that is not a, that is very easily, you can measure it today. If you want to give there are analytical tools which can very easily figure that out. There was a movie once, I think that movie was Coma, and where they said if you do carbon monoxide poisoning, it is very hard to figure out.
Robin Cook's novel, Coma. That is putting carbon monoxide in the blood supply.
In the operation theatre or this thing.
So don't give too many ideas.
Yeah, that is. But no, what I'm trying to tell you, what I'm telling you, even there it can be found out. Because today we have analytical tools. And therefore the answer to your question would be, it would not be possible because chemistry has gone to such a point where you can estimate even nothing. If I have nothing, I can estimate it. So we have got I'm just trying to exaggerate my point. But what I'm trying to make is extremely small concentrations. We have the analytical tools to figure it out. And therefore, the question that you raised, it would be very hard for anybody to do that. Because chemistry will find you out.
Then chemistry had a loophole to erase the blood stain also.
That's right.
We have one question.
Then chemistry had a loophole. Then chemistry had a loophole to erase the blood stain also. It can also extremely it can found out in the sense. It can a loophole to erase it.
See, at the end of the day, whatever you do to erase it, earlier, you do, let's say, a few washes, you might leave behind 5 ppm. And let us say in those days, 5 ppm could not be found out. And therefore, that guy would get away. Today, you can find out 5 ppm. You can find out 5 ppb, you can find out 5 ppt even today. So, which means, after committing whatever acts that person did, you would have to spend the rest of his life cleaning this place up. And that's basically what it is. Because any cleaning process is asymptotic, You clean it little less, clean it then a little less. But you're not going to ever get rid of it completely. That's basically what it is.
So we have one question from the remote participants. Good evening, sir. To convert the concentrated H2SO4 into a diluted state, water will mix it. What kind of chemical reaction takes place in that process?
Okay. That is basically, it's a dilution process. That's what we call the heat of dilution. And that heat of dilution is extremely large, and that's the reason why when you add sulfuric acid to water, you're doing many things. You're breaking the bonds between water, which is hydrogen bonded stuff. You're breaking the bonds between sulfuric acid and so on, and therefore you're causing solvation of these molecules. And in that process, you have to break many bonds, and the net effect is you're putting out heat. And that's a lot of heat. The heat of dilution in that case is quite large. And that's the reason why we always say you have to add sulfuric acid to water and not water to sulfuric acid. That is safety measure. And it's essentially because of the fact that the dilution process that you are causing involves a lot of heat. And that heat is enormous.
There is one more explanation for this. In a book, Experiments Without Explosion, by Russian book, they talk about the density of the sulfuric acid, which is something like coconut oil, something like that.
Yeah.
So if you add one drop, because it goes deep inside the water, it is everywhere surrounded by water, the heat is simply absorbed by water.
Yeah.
But if you do it the other way, it forms a layer on top of it, it splashes out, giving all this nonsense.
That's right. That's the most See, I was working in an industry and where we had to do this dilution, and the people who are running the machines, they would have to get this to go. But the explanation that I would have to give them in a way that they would understand was the following: that if you add water and you put sulfuric acid, and even if it splatters, what splatters is dilute sulfuric acid on you. But if you do it the other way around and if it splatters, what splatters on you is concentrated sulfuric acid. Therefore, don't do it. Do it this way. I thought this way they would remember it much more. And of course, I could talk to them about the density and issues and so on. But the thing was that in sulfuric acid being added to water, any splash would be dilute sulfuric acid on you, which is perfectly far better than the other way around. But what he's saying is important. It's also an issue, but an important issue for the density of the sulfuric acid being so much larger that it would just go in and then float and the water will come out.
So we are closing down now. So we have been asked to complete it by 6 o'clock. So we are 15 minutes over. Yeah, couple of things. One is, some of you may want the certificate. Now we have automated the certificate process, provided if you are filling up the feedback form, your certificate will automatically generate and dispatch you. Please fill up the feedback form. You will get the certificate automatically. If you are choosing the checkbox for the requirement of the feedback form, certificate, you can just check it. You will get the certificate. So we have the Google group as well as the Telegram group, WhatsApp group. Become the member of all these things. Now we will get notification from our events, of our programs. And our next PSL program is going to be in University of Madras Taravani campus. It's going to happen on 8th of January. So there was an interesting treatment done for cancer. So they did the treatment through gene editing. It's going to be taught by Dr. Indumati Mariappan from LV Prasad Eye Institute, Hyderabad. And we also have one more cancer institute specialist, Dr. Priya Ramanathan from Adayar Cancer Institute. Both will talk about that. It's also going to involve a lot of chemistry. So those who are interested in chemistry, it's going to be a biochemistry. Please come attend that one. It's going to be on Sunday. Please note that it's going to be on Sunday, 4 o'clock. So we will send the notification to all this. So let me wind up by saying the vote of thanks. Anyone? Vote of thanks.
Thank you all. Viswanathan sir, thank you for the experiment. In PSL, so far we did the theoretical explanations. I think this is the first time we are conducting the experimental event. So I'm also very excited. Even though it's all a basic chemical reaction, mostly we done in the theoretical things, but currently we saw the both theory and the practical things. So thank you for that, sir. Also, Nadu sir, thank you for that. So, to organize this event, we are thanking Anna Senari Library Management. Thank you all. For next event, you will receive a notification soon. Please participate. Thank you all.
Thank you very much. It's one of the exciting event we have done. PSL, although we have 56 to climb, I would say that maybe 5 to 10 is going to be very exciting. The participants are very much excited and they are part of their event. This is one such thing. Thank you very much, sir. We will have more such thing in future. We will also organize a Chitrai Fest in April for summer camp for the students. So that's going to be, we are planning it and we will announce it soon. Definitely we will include the chemistry as well. Thank you.